So far, okay, what we've seen are the different typical probabilistic experiments. So rolling a die, tossing a coin. Um, there's also experiments we'll see like playing with cards. We've seen sampling from an urn and so on. Those are, typical potential probabilistic scenarios where we can run our experiments, okay? Once we know that, let's study a little bit more what different types of probabilistic distributions we can have. And what can we do with the data frames that we have defined? What can we do with different sample spaces that we have defined? When we talk about random variables, okay, we are talking about variables whose values in the sample space can be discrete, like tossing a coin, like sampling from an urn, or can be continuous, like what's the height or what's the temperature, okay? And we're going to be talking about two types of distributions. Right now, we have defined how we can create, the sample spaces for discrete events. We'll explain how we can create sample spaces for continuous events, which is just a function, okay? But we will also talk about the different types of distributions. When we talk about discrete distributions, a discrete distribution assigns a probability to every event in the sample space. So imagine we are tossing a coin. We have two different potential possible events, okay? So for each of the potential events, we assign a 50% probability. An important characteristic, both in discrete and in continuous distributions, is that the sum of the whole distributions across the entire space of events must sum 1, okay? So in the case, for example, of a dice experiment, where you have potential values from 1 to 6, the sum of all the probabilities has to equal 1. In the case, for example, of tossing a coin, the sum of the two events, okay, being head to the toes, it also needs to add up to 1. What is an event? When we talk about events, okay, we've talked about sample space. So the set of events defines the sample space. An event is basically a collection of outcomes to which a probability is assigned, okay? So in reality, an event is a subset of the sample space. Okay? An event can be getting a 6 when we roll a die. An event can be drawing a black card from a deck of cards. Okay? An event can be drawing a king of hearts from a deck of cards. Okay? Anything that happens when we are experimenting with a probabilistic experiment, that's an event. Okay? And actually the collection of events is what defines the sample space. And each event is going to have assigned a given probability. It can be a simple probability because it's just one event, and if it's a subset of events, it will be a more complex probability that we'll look into how this can be computed. As I was saying, okay, if we talk about something like what's the probability of getting a 1 when we roll a dice, we know that it's 1 out of 6 different potential events. Okay. However, there are more complex distributions of events. Okay, if it's not just like one single event, but if it's a collection of different events that we want to understand the probability of happening, then we need to use different types of distributions. In this class, we are going to see joint distributions, conditional distributions, and unions. Okay, so when we are again looking into subsets of events, not single events, we can be talking about a joint distribution when we are looking into whether a couple or more events happen at the same time. So for example, what's the probability that we are drawing a red card that is also a king? Conditional probabilities define a temporal time frame. Okay, so what's the probability that something will happen before something else happens? Or what's the probability that something will happen after something else has happened? Okay, so for example, what's the probability that I draw a king from a deck of cards and then I draw a card that is red? Okay, and that's what we call a conditional probability, and it's defined through that formula. And then we're also interested in unions. So what's the probability that one thing or the other will happen? And it's basically defined as the sum of the independent probabilities minus the intersection, minus the joint distribution. And again, these are distribution of events when we are talking about subsets of events, not single events. So let's delve a little bit more into joint distributions. say we have two random variables, which are x and y, okay, and these two random variables are independent. If they are not independent, then the joint probability becomes a little bit more complicated. We'll talk about the chain rule, okay, but for the moment, if we assume that they are independent, like for example, we roll a dice 3 times, we know that, the number that we get from a dice is going to be independent from when it's that we are rolling it. Is it the first time that we roll the dice, the second time, the third time? If the roll is fair, the events are going to be completely independent. However, we might have dependent events, okay? So for example, the fact that there's traffic jam on Beltway, it's probably highly related to the fact that there's either bad weather or that there's a baseball game, okay? And in those cases, again, the joint distribution will be something that's slightly more complicated, and we'll look into that at the end of the class. That's what we will be looking into: chain rule and Bayes rule and Bayes rule and so on. But for the moment, let's assume that the events are independent. Let's assume that we toss 3 coins, okay, and we want to understand what's a joint distribution probability. Okay, if you look into that, basically, what's the probability of getting heads, heads, and heads when we toss a coin? It's 0.5 multiplied by 0.5 multiplied by 0.5. Why? Because basically, if we go back at this formula, the probability of 2 events happening is the product of the 2 probabilities of the 2 independent events. Okay, so in this case, the probability of having heads for 3 coins is the multiplication of the individual probabilities of the heads event happening. Okay, so the probability of getting a head when we toss a coin, it's 50% of the time, it's 0.5. Okay, and that happens 3 times. So it's the multiplication of the 3 independent events. And again, these events are independent. That's the reason why these probabilities are like that. Okay, and we can apply the joint distribution formula. It turns out that, all these things that we need to understand from a conceptual point of view can be done automatically in R. Okay, remember again that we have the functions toss coin, roll die, and so on. So we can actually understand what are the joint distribution probabilities. Let's define an event, okay, which is going to be toss coin. We are tossing 3 coins, and we basically say make space equals true. And what we managed to do with this function is that basically we are creating the whole space of potential different subsets of events happening, okay? So what you see here is that we see the 8 different scenarios that might happen when we toss 3 different coins, okay? And the probability for each of the events. So as you can see, there's no need to manually compute the joint distribution probabilities for the different events that happen when we toss 3 coins, but rather we can use R. And we can do the same thing exactly for when we roll a die. Okay, so you can say, let's roll a die. Let's have two dice. Let's make all the space. So I want to see all the event space here. And the event space in this case is going to be 36 different events. Okay, so you roll 2 different dice. You might have 36 different events, having 1 and 1, 2 and 1, 3 and 1, 4 and 1, which is different of having 1 and 2 and so on. Okay. And then we have the probability for each of those events happening. If, of course, the event space is too large, we can always access. Remember that these are data frames, so we can also access. So for example, we could say, okay, let me access, just what happens. Let me just see the 3 first potential events that happen when I toss 3 coins. Okay, so you would see the 3 first rows with all the columns. And you can also see, just give me, second, third, and fourth columns and things like that. So you can play with the different ways we've seen to access data frame information. Okay. And also another thing that I recommend you to do is basically playing around with different probabilities. So far we've always been talking about having fair coins. Okay, coins that have exactly the same probability, but you can also define event space in which the probability of getting one or the other event might not be equal. Okay, so in this case we would be defining to getting heads 70% of the time, or when we toss a coin getting tails 30% of the time. Okay, you can play with that. Other experiments that we can run to understand joint distributions, let's continue with the example of having a deck of cards. Okay, so the first thing that we can do, actually R allows us to define having a deck of cards. So let's create, that deck of cards. If you explore S now, you'll see that we have 52 different cards here. You have the suite being clubs, diamonds, hearts, and spades, and then you have the rank, which is basically the number for the suite. Okay? Okay. We can basically create different subsets for the joint distribution. So for example, imagine that we have this deck of cards and we want to see, okay, I want to basically select all the cards here that are just heart. Okay? So you could do something like, okay, give me the subset from S that the suit is actually equals to heart, okay? Or for example, give me a subset of cards whose rank is in values, what's the example that we're doing here, in values like 7 to 9, okay? So basically what we're creating here are different subsets of events, okay? And we can make this even more complicated and select, subsets of subsets and so on. But basically what the subset command allows us to do is to select a subset of cards given the whole card deck of 52 cards. Okay, and that's going to be important to compute different joint distributions. So for example, once we have these, we can say, okay, so what's, for example, the intersection between, so let's define these two subsets, okay, subset A and subset B, and then we can define all different types of experiments. So for example, what's the intersection between event A and event B, okay, so the intersection between the two, if we have all heart cards and we have all cards ranked between 7 and 9, are basically, the hearts that are ranked between 7 and 9. Okay, that intersect is basically the joint distribution. What's the joint distribution? That it's a heart and that the rank is between 7 and 9. Okay, so we are here actually computing, the set of events for the joint distribution. What's the union? Okay, that A and B happen. Okay, so we want, basically we want the cards that are A heart or whose rank is between 7 and 9. This is a union, okay? This is basically a union event. So we've seen the joint distribution, the union distribution, and we can also say something like, okay, what are the differences between the two? Okay, and the difference between the two are basically the hearts whose numbers are not between 7 and 9. So this is just to give you, another example of how is it that we can play with joint distributions also in R. There's no need, again, to define in general unless it's a very weird event space or a very weird probabilistic problem. In general, you'll be able to have already the event space defined in R, and you'll also be able to compute the different types of distributions in R. Okay, so let's do an exercise, okay? This is the exercise that I proposed. Before you turn to the next slide, make sure you at least try to execute it, okay? We're going to continue working with the deck of cards, so we have 52 cards, and we're going to propose an experiment that consists of drawing exactly one card, okay, and let the outcome be the face of the card. So we want to define we're going to define two events, one of drawing an ace and the other one of drawing a club, and we want to compute what's the probability of the joint event and what's the probability of the union. Okay, so what's the probability that we will draw an ace and a club, and what's the probability that we will draw an ace or a club? Okay, so make sure you understand it. Try to make it either numerically or with R commands. Okay, and then basically now stop the video, think about the exercise, and then continue with the video. Solution. So the probability that, we have an ace, it's basically we have 4 aces out of 52 cards, so it's 4 over 52. We have 13 clubs, so it's 13 over 52. Okay, and then what's the probability that the ace is going to be a club? So there's only one card, okay, which is an ace and a club at the same time. It's the ace of clubs, in fact. So basically the probability that it's A and B, so the joint distribution, is going to be 1 over 52. Okay, and then the probability that it's either one or the other, as we mentioned before, it's the sum of the individual probabilities, the independent events, plus the probability of the intersection. Okay, and that's what you get for a number. Okay, for we continue, there's also an important concept which we're going to be using in the future classes, which are called marginal distributions. So given a joint distribution, what if we're only interested in the distribution of one of the variables? So marginalization is basically the one that allows us to compute this type of distribution over small sets of variables. What do we mean by that? So imagine that we are trying to measure the temperature given a certain type of sunny or cloudy weather, okay? The probability that the temperature is going to be hot when the weather is sunny is 0.1. Probability is going to be, temperature is going to be mild when the weather is sunny, it's going to be 2%, 20%. It's going to be cold when the weather is sunny, it's going to be 10%, and so on. We can marginalize on a given feature. In this case, we would marginalize on the temperature, okay? And what we do is basically we sum up all the probabilities for each of the features given all the different types of weather. So in this case, what we would do is fill out the table with the sum. So the temperature being hot, the probability is 15%, temperature being mild, probability is 55%, temperature being cold, probability is 30%. Okay, so marginalization corresponds to summing up all the dimensions in the sample space. And very importantly, the new table also needs to sum up to 1. Okay, remember that all possible events in a space of events for a given experiment, a random experiment, it needs to sum up to 1. Okay, so here again, if you look at the marginalized table, the sum of the probabilities is still 1. We can also marginalize on the temperature. So think about what would be the probability for sunny and the probability for cloudy. Again, we need to sum up. In this case, we would sum up all the different temperature events for sunny, all the different temperature events for cloudy. Okay, it would be 40 and 60, and again, the sum of the marginalized table, the probabilities in the marginalized table also needs to add up to 1. Okay. So again, there's also a way of doing all these things in R. So we can compute the marginal distributions in R using the marginal function. Okay. So imagine that we defined again a toss coin event in which we toss 2 coins. We can compute the marginal for toss 1 or the marginal for toss 2, and which we'll basically do, we'll sum up all the different potential outcomes for toss 1, okay, which are head or tails, or it will do the same thing for toss 2, and it will add up the probabilities too. Basically, we can go back to the tossing example. Let's define again, let's toss a coin. Let's toss, 2 coins. We create all the event space, and this is the possible event space, and then we say, okay, we want to marginalize on this event space, and specifically we want to marginalize on a variable called toss1. Okay, let's continue with different types of probabilistic distributions. So far, in the first part, we have mostly discussed joint distributions, that is distributions in which we are looking for events that happen together. Okay, so for example, A happens together with B, or A or B happen for unions. Okay, for the second part of the class today, we're going to be looking more into conditional distributions. Okay, with different types of complexities, but in general, we're going to be looking into events basically that depend one from another. Okay, so in general, conditional distributions are basically computing the probability that an event happened given that another event has already occurred. Okay, so in this case, for example, what we are seeing here is what's the probability that the event A will happen given that we know that B has already happened. Okay, we know for a fact that B has happened. What's the probability that A will take place? And that's defined as, you know, that quotient that you see there, which is the probability of A and B, so the joint probability divided by the probability of B. If we look graphically, trying to understand why is that formula, the formula to represent conditional distributions, or why is that the correct formula, basically if you look on the left-hand side, we have 2 different event spaces. We have A and we have B. Okay, A is the circle, the ellipse, and B is the square, and we analyze what's the probability that given that we know that B happens, A is going to happen. Okay, that's the conditional probability of B, A, given that B happens. So we know that we are in the green squared space, what's the probability that being in that space A is going to happen? Okay, so the new outcome space is the one that you see on the right hand side. That's what graphically the formula represents. For example, what's the probability that the sum of two dice is 6 given that the first is greater than 3? So we throw two dice. The first one, we get a number larger than 3. What's the probability that the sum of the two will be 6? We're going to be looking into how we can solve this manually, but also with R. Okay? How would we solve this manually? Basically, we can look at the whole space of events. We can evaluate what are the different possibilities for the first dice and for the second dice. Okay? A can have values from 1 to 6, and B can have values from 1 to 6, as you can see in the table. And the number that appears in the table is the sum of the two values. Okay, so if A, say, second row, first column, means that dice A equals 2, dice B equals 1, and the sum of the two is 3. We want to look into the conditional probability that given that we know that the first dice is greater than 3, what's the probability that the sum is going to be 6? Okay, so basically we're looking at, this P of A greater than 3 and B, given that A equals 6. Okay, given that A is larger than 3, what's the probability that B and A equals 3? Okay, we are looking into that joint probability. In order to do that, basically, we have to look into, first of all, what's the probability of the fact that the first dice is greater than 3. And we also have to look into the probability of the fact that is greater than 3, the first one, and the sum is equals to 6. Okay, so what you see there is the general formula. Then the first one is the numerator, so the joint distribution. And then the second one is the enumerator, the denominator. Okay, so the second part of the quotient. And then basically the last part is going to tell us what's the conditional probability. How do you solve this? So first of all, the probability that given that A, or the first dice, is larger than 3, the sum is equals to 6. It's basically what we need to do to solve this. We need to take a look at the bottom part of the table. The three last lines of the table, A equals 4, A equals 5, A equals 6, represent all the possible values for which the first dice is larger than 3. Okay? And if we look there at the 3 rows, we see that there are 2 cases in which the sum is 6. The case in which the first dice is 5 and the second is 1, and the case in which the first dice is 4 and the second is 2. Those are the only 2 cases. Okay? So basically have this case here for 6 and this case here for 6. So then we go ahead and say, okay, so the probability, the joint probability that the first dice is larger than 3 and the sum is equals to 6 is 236. Okay, because out of all possible 36 events that we have in the table, these are all 36 events, out of those 36 events, only 2 follow this condition. Only 2 follow this joint distribution. This again is the numerator here. Okay, so the joint distribution of A and B is this one. And then we have to look into, the probability that the first dice is actually larger than 3. Okay, and the probability that the first dice is larger than 3 is in fact 3/6. Okay, so out of all, the different values that the first dice can take from 1 to 6, okay, we have 3 different cases in which it can be equal to or larger than 3. Okay. Okay. And then finally, the way we solve basically the conditional probability, it's this one here, the conditional probability that given that A is larger than 3, the sum is going to be equals to 6, is basically dividing the joint distribution by the independent probability. So we divide 236 by 36, okay? And that's the conditional probability. So basically the formula for a conditional probability is based on the joint distribution and on the probability of the independent event for B, for the given fact. It turns out that we can do this in R, okay? So we can define, for example, if we continue with the rolling a dice example, basically we can create the space of events, okay? Rolling 2 dice. And once we do that, what we can do is basically compute the probability that these events will happen, and that's what we are doing with the command addrb. What we are doing there is basically summing the two probabilities in the space of events, and then basically we can extract how many times a given situation where A and B happen takes place. Let's start. Okay, again. We use the command roll die. So is again, we're gonna save roll die. We roll 2 and we make the event space. Okay, we take a look at the space of events. In fact, we have 2 dice, and what we have here are, the different numbers that we can get and the probability for those events. Then the next command, what the next command is doing is basically saying, okay, so let's take, that space of events, that data frame. We're going to apply a function to that data frame, which is going to be the sum function. The input variables for the sum are going to be x1 and x2, okay, which are basically columns 2 and 3, so the numbers that we are getting with the dice, those are going to be the numbers that we're going to sum up. And basically the column, or the name for the column we are creating is going to be sum. Okay, so if we take a look at T, what you see here is that, for each of the possible events that we observe, what we're doing is creating a column called sum, okay? Take in mind that, what we want to compute here is what's the probability that given that when we roll a die, the number is 3, when we roll two dice, the sum is going to be 6, okay? So we want to compute what's the sum of rolling the 2 dice, okay? So here, this column that we are creating with addrb, it's basically a function that allows us to, do some data management over the frame that we have. And in this case, we are summing up these 2 columns. Okay, take a look. Basically, here we had, the space of events, and we are adding another column to the space of events, which is the sum of the 2 values. So 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is 5, and so on. Okay? And basically what we are doing is, because, taking a look, these are the 36 events. This is basically the matrix of events that we have already explored, but taking a look at this space of events is kind of difficult. So what we're going to do is create a matrix, and this is something that we already did in the previous class. We are creating a matrix with this data frame such that, we're going to have, the matrix is going to have all the elements, and the elements that we're going to have in the matrix is basically going to be the value sum. And we want to have a matrix that has 6 rows and 6 rows, and hence 6 columns, because we have 36 events, okay? So what we're saying here is basically take all the elements from the space of events that we have, okay? Divide the 36 events into a 6 by 6. And put into each element in the matrix just the value from the column sum. Okay, so we are literally creating the table that we saw before, in which A equals 1, A equals 2, A equals 3, B equals 1, B equals 2, B equals 3, and so on. And this is the table. And for example, when die 1 is 6 and die 2 is 6, the sum of both is 12. Okay, so we are creating that table in R. Okay, and now, for example, if we want to see, okay, how many times in this table that we have created, okay, how many times the sum of the values equals 6, okay? So basically, what's the probability that, the sum of the two, of rolling the 2 dice is going to be equal to 6 is this command that you have here, okay? So what we have in this command is basically saying, take the table M that we have created. So let's write. So we take the table M that we have created, okay, which is M, access the elements, the row 4 to 6, okay, and create a table with the elements that are equal to 6. Okay, so basically what this is telling us is that, in the 6 by 6 matrix, if we take a look at the 3 last rows, which are the rows in which A is larger than 3, the sum is equal to 6 only in 2 cases. In fact, that's what we saw before. Okay. And then what we do is that we divide basically by the dimensions of this table, which is what dim and dim1 and dim2 are doing, okay? So basically, in order for you to fully understand what I'm trying to do in these slides, so let's take a look at this table here, okay? Computing basically this probability of, what's the probability that the sum is equal to 6, given that a is larger than 3, this 236 is something that, we can compute with these commands here. Okay, so this is the joint distribution. And then once we have the joint distribution, we divide by the probability of b, the probability of a being larger than 3, okay? But, these are the different functions that we need to use in order to compute that. We can even go beyond that. So far we've seen joint distribution and conditional distributions, but we can even combine them further. We're going to be looking at what we call the chain rule, okay, and Bayes' rule, although Bayes' rule is something that we'll further look in the following classes. But basically the chain rule defines the joint distribution of events x and y as a product of conditional distributions, okay? So remember that when we defined joint distribution of two events, we said, okay, what's the probability of a card being red and being a number 8, for example, okay? So we said that, if these are independent events, then we know that the probability of x and y, the joint distribution, is going to be the product of the two independent distributions. Now we are looking into a slightly more complicated scenario in which the joint distribution is based on events that are not independent. Okay, so x and y are not independent. And when x and y are not independent, the joint distribution is expressed using conditional distributions. Okay, specifically using the formula that you see there. So the joint distribution is going to be based on the probability that y happens and on the probability that knowing that y happens, x takes place. Okay, so it's an independent distribution and then it's a conditional distribution. That's the way we define a joint distribution when the events are not independent. If x and y are independent, in this formula here, the probability that x happens given y becomes the probability of x, and then we have the product, okay, px by py, which is the original definition of a joint distribution when the events are independent. Let's take a look at an example. If, we have this tree here, okay, that starts with play, what's the probability that given that play happens in a sentence, it is going to happen, okay? Then we go to it. What's the probability that given that we know that play happens and it happens again is going to appear in the sentence? And then if we go to again, what's the probability that knowing that play, it, again are words that appear in the sentence, what's the probability that Sam is going to appear? Okay? So basically this is a tree that we build in order to understand the probability of different subsets of words. This is something that, for example, Google uses when you are searching for things in Google. They try to fill in your sentence and they use different probabilistic models. Now, the probability of, knowing that play, eat, and again appear in a sentence, Sam will appear, can be expressed as a product of different probabilities. So it can be expressed as a product of the probability that play happens, that it appears in the sentence given that play appeared, and that again appears in the sentence given that play and it appeared. Okay? So in general, and this is the reason why we call it chain rule, for the general case, the way we express that probability, which is the joint distribution of different events happening, is going to be based on the product of different conditional probabilities. And this is also related to Bayes' rule. Okay, we are going to be looking into naive Bayes classifiers in class 6. So, this is a concept that you need to, understand. But basically what Bayes' rule says is a way or a function, a formula to compute this conditional distribution. Okay, so given that, we know that an event A has happened, what's the probability that B will happen? Okay, this is a conditional probability. And in fact, this conditional probability can be solved with the formula that you see there. Okay? What you see in the enumerator, basically, when we looked into conditional probabilities, in the enumerator we said, okay, we have to compute the probability of the joint distribution, so the probability that A and B will happen, okay? If the events are independent, in fact, it's going to be easy. It's the probability that A happens and the probability that B happens, so it's a product of both probabilities, okay? But if they are not independent, the joint distribution in the enumerator is basically a conditional distribution that is basically a joint distribution that has to be solved with the chain rule. And what we do is we apply the chain rule. Okay, and in fact, what you see there is the probability that A and B happens is the probability of B, and the probability that A happens even that B happens. Okay, is this clear? So what we're doing here is basically what Bayes' rule is saying is a way of defining a conditional probability given that the joint probability that we have here is not based on independent events. And so the joint probability here is going to also be based on a conditional probability which is expressed or solved through the chain rule. We'll see more examples on how this Bayes rule is used, but basically just bear in mind that this is the formula that needs to be used every time you wanna solve this type of probabilistic function. Okay, so every time you have this conditional probability, bear in mind that the joint probability is translated into a chain rule. Okay, so how can we express this graphically again? So in this case, we are starting, okay, the probability that, A happens given that we know that B happens, which is the example that we saw for the conditional probability, okay, that's the graphical representation. But now what Bayes' rule is saying, okay, so, we need to add to that the fact that given that B happens, what's the probability that A is going to happen, okay? Which is what we see in the second representation. And then we need to add to that, okay, given that we know that A happens, what's the probability that happening B, A is going to happen, okay? So that's basically what Bayes' rule is represented, can be represented graphically. What Bayes' rule is represented is when we have a conditional probability of events that are not independent, okay, the joint probability has to be represented as a chain. And thus this chain here, okay, is going back to the probability that the event A will happen given that B happens, but based on the fact that A happens, okay? And this is the reason why we go back to the whole ellipse representation.